Stephen, who will talk about Switchboard, a framework for hardware-software co-simulation, as I understand it.
All right, thanks. So I'm Stephen Herbst. Just wanted to give a little bit of background about me. So I actually started off as at the beginning of my career as an analog designer, but over time became kind of fascinated with the simulation aspect of that work and got into mixed signal simulation, and that brought me into the digital world and the software world. And these days I am working on emulation at Zero ASIC. So at Zero ASIC, we're building a library of chiplets that can be tiled together to form complex systems. And what we wanted to be able to do is for a given configuration of chiplets, we want to be able to simulate that entire system and use it for software development. So this needs to be a very fast simulator, and because we want to do complex things like booting Linux or running ML models. And we also need to be able to work with a very wide range of models for the different chiplets in our system. So for example, we might have RTL simulation of one of the chiplets. Maybe for another chiplet, we have implemented it on an FPGA to speed up the simulation. But in other cases, maybe it's more at a conceptual stage. Maybe we just have a Python model or a C++ model. And of course, at some point, we'll also have physical hardware that, so maybe we want to have a blend of some physical chiplets and some chiplets that are just defined in Python, and we want to, all of those different combinations to work together. So the solution that we came up with, and what I'm going to talk about today, is called Switchboard, and it's a framework for wiring up all of these different kinds of models. And so this includes RTL that's simulated and emulated, different software models, and maybe not surprisingly, given my past, also SPICE models. So this is a open source project. You can find it on GitHub. It's also pip installable. This brings us to the outline for the talk. So I'm going to start by just describing what's the architecture for Switchboard. I'll show a code example so you can kind of get a sense of what it's like to work with Switchboard. I'll talk about interfacing with standard digital interfaces like AXI. If there's time, I'll talk a little bit about mixed signal simulation and then just show a few real-world results. So the basic building block, or the basic unit of communication in Switchboard is the Switchboard packet. So a Switchboard packet has up to 52 bytes of data payload, and then it's also got an integer destination that's used for routing, and some optional flags that are used to optimize performance. So these Switchboard packets are conveyed over Switchboard connections, which kind of mimic a physical hardware communication link. So they have the following properties. So they're fixed, unidirectional. They're single producer, single consumer, meaning that you can only have one transmitter and one receiver for each link. And they're also latency insensitive. So in the in the hardware world, what this interface looks like is just a familiar ready valid interface. So it's we've got the data destination and flags fields that I mentioned about, ready valid handshaking, and this clearly meets the properties that I described for the Switchboard connection. On the software side, the packets are conveyed through shared memory queues, so we have one piece of software that's sending a Switchboard packet into the queue, another piece of software that's receiving packets from the queue, and this also has exactly the same properties as the ready valid interface that I was just showing at the hardware level. So the interesting thing is what happens when we want RTL to talk to software. Well, in that case, we can instantiate a module that on one side has the hardware ready valid interface, and on the other hand, through DPI or VPI, is able to send and receive switchboard packets into one of these shared memory queues, into memory that's accessible by the software that's trying to talk to it. So kind of surprisingly, if we want to, instead of simulating this RTL, instead run it on an FPGA, the situation looks, at least conceptually, is almost exactly the same. So we instantiate a module in the RTL that has a ready valid interface on one side, and then instead of VPI or DPI through PCIe is able to read and write packets into a shared memory queue. And part of the reason that this works is that we've kept the format of this shared memory queue to be standard and simple, so that it's relatively easy, or it's at least feasible to interact with it through RTL code. So let's say in your system, maybe you don't have PCIe access to memory, you have some other way that you access it. We've tried to keep the specification for the queue simple enough that it would be possible to create a new RTL implementation to drive packets into a queue in that case. So the takeaway from this is that if you want to plug into the Switchboard ecosystem, you just need to be able to read and write these queues, and you kind of automatically get to connect to all the other models that are Switchboard compatible without having to make special adapters for I don't know, say from how to talk to a RTL simulation from an FPGA emulation or something like that. So let's take a look at kind of how does Switchboard work from a practical perspective. So in this simple example, I'll just this is almost as basic as it gets. We just have a Python program where we want to send a packet, a Switchboard packet, into an RTL simulation, see some modification of that packet, and send that back to the Python code. So on the RTL side, we start off by including the Switchboard header file, which provides some macros that just make it easier to set up these connections. So, for example, there's a macro to create a bundle of wires that corresponds to the Switchboard interface. There are also macros for creating both the transmit and receive directions of a Switchboard connection. And I guess one thing that I haven't mentioned up to this point is you can see that the very last argument to those macros is a string, which is a file name, and that's the way that we refer to these different shared memory queues, is that they show up as memory map files that, as long as two things are referring to the same file, then they're connected together through a Switchboard connection. On the Python side, the way that this works is the Switchboard connections are established by creating objects that correspond to either a packet driver or a packet receiver. And you can create Switchboard packets by also just creating an ordinary Python object where the data payload is just a NumPy array. So this is kind of a convenient, convenient to work with in a variety of contexts. And then you can just send and receive Switchboard packets. The Python interface is very convenient for doing prototyping and setting things up quickly, but occasionally we do need something that's a little bit faster. So Switchboard also provides a C++ interface that has kind of the same abstraction of being able to create objects that set up Switchboard connections and work with the Switchboard packets that are sent across those connections. So I'd like to talk now a little bit about how to operate with higher level interfaces when using Switchboard. So the Switchboard packets are great for kind of general purpose communication, but in a lot of cases there's already a latency insensitive interface that's standardized that's being used in the system. So for example, AXI is a widely used one. So in that case, the general strategy is you take each one of the latency insensitive channels that's present in that interface. So in the case of AXI, there's 5 channels. You map each one of those to a Switchboard connection, and then just concatenate the bits that are in each channel and send those across as payloads of the switchboard packets. So in general, this can be done for any latency insensitive interface, but for some of the particularly important ones, we've already built that into Switchboard. So for example, AXI Lite, these already have built-in support for Switchboard, as well as the Universal Memory Interface, or UMI, which is open source and awesome, and Andreas is going to talk about that this afternoon. I think just for this talk, since AXI is maybe familiar to some more folks, I'll just show an example of how to work with that. So it looks very similar to using the sort of native switchboard packets, where there's macros that are available to create the connections, and in this case, we're actually not just creating a single connection, but we're creating several connections that correspond to the different channels that are in the AXI interface. And similar story on the Python side, but one difference I wanted to point out here is that the abstraction level is raised for things like AXI or UMI, where instead of just working with individual data payloads that are coming in single switchboard packets, the interface is instead more of a memory read and write interface, and more like a mem copy, where you either send a NumPy array to an address, and in the case of AXI, under the hood, that'll get diced up into one or more bursts to transmit it efficiently. Or in the case of a read, then you just say, here's the memory that I want to read, here's how much I want to read, and what you get back is just a single NumPy array with the data, even if under the hood it takes a number of transactions to collect all of the data. So I think I'm running a little bit short on time, so I'm going to go through this pretty quickly. But it might be, the idea of running mixed signal simulation probably seems kind of disjoint from what I've just been talking about. But it does broadly fit into the same, into the same area of trying to support a wide mixture of hardware models and simulate them all together. And we found that Switchboard was actually a pretty good place to implement this functionality, because we could leverage our existing build automation. So we're just very briefly, we're using Zeiss, and that can be combined with either Verilator or Icarus Verilog. The idea is that you can take a SPICE subcircuit, just instantiate it in Verilog, which normally doesn't work, but we've kind of used our build automation to try to make that as seamless as possible, and then define basically the A to D and D to A rules for connecting between the SPICE subcircuit and the rest of the Verilog simulation. So that's kind of that's a fast overview of what Switchboard does. How does it work in the real world? So I guess the shared memory queues themselves are very high performance. So each one of those connections can run up to about 1 GB per second and has latencies that are just a few hundred nanoseconds. So the thing that's cool about this is if you're running a really fast Verilator simulation of a small design, you can actually keep up with that through switchboard connections on a cycle-by-cycle basis. At a much higher level, we've used Switchboard to build a web app that you can try out for yourself. It's at zeroasic.com, where you can drag and drop chiplets and spin up a simulation of your custom system on Interposer, and boot Linux on it. It takes a couple minutes. So this is kind of a demonstration of the fact that on the one hand, it's very flexible and quick to set up, but it can support these very high performance use cases, like trying to boot an operating system on multiple chiplets. So that's all that I've got today. If you're interested, please check out the GitHub repo. Thanks.
Steven, so we have questions here. Let's start with Tim.
Do you have integration with things like QEMU or other very high-level simulators?
QEMU, yes, it's we have done that. I think it's not sure if it's part of the GitHub repository or the publicly released stuff, but we have done that.
Could you say something about what FPGA boards you can support on this?
Yeah, so we F1. So we're doing this is so far we've been working with cloud FPGA emulation.
On F1, okay.
Yeah.
All right, thank you. Yeah, this would be, for each different FPGA vendor, you have different sort of facilities to get across that host to FPGA boundary. This would be a great bridge that takes away that problem.
Yeah, definitely. I think there's a question behind you.
You mentioned Axie. What about Wishbone?
Not yet, but I guess if there's interest, I think it would be doable.
Anyone else? We're at lunch break now, right? So before.